Hello everyone. This is my project predicting the remaining useful life on NASA turbo engines. So the goal of this project is to predict the number of time cycles that an engine will continue to operate before it fails. In other words, RUL. And I used linear regression, SVM regressor, and random forest regressor. So what is RUL? RUL is the number of operation time cycles that are remaining before an equipment fails. And why are we interested in it? Because once we know RUL of equipment, we can avoid unscheduled repairs, optimize maintenance schedules, and enhance safety. So I got this data set from Kaggle, and um, here I here I describe the data structure, the objective, and the data format of the data set. And here I imported all the required libraries first up. So pandas and numpy for data manipulation, matplotlib and cbond for data visualization, and then some libraries from sklearn for scaling the data, for splitting the data into train tests, and also for evaluating our models. Here I loaded up the training data set, and here we can see that the last two columns are all NaN values, which are obviously not important for us. So I removed them from the data set. And here as well, we see that there are no this data set has no column names. So from the literature, I got these column names. The first one is unit number or the engine number. The second one is the time cycles. The next three are the operational settings, and followed by the sensor data for the next 21 columns. So I gave the column names here, and here we have the column names for the training data set. And I did the same for the test data set. The last two columns are all NaN values, so remove them and then gave them the column names. And here I am looking for NA values in the training data set. Clearly we don't have any NA values, so we are good to go there. And here uh, these are the statistics for the time cycles. So here we see that the maximum time cycles that any engine has ran for is 362 time cycles. And then the minimum time cycles that an engine ran before it failed is 1. And here this is a visualization which shows the time cycles that the maximum time cycle that a particular engine has ran for. So here we have time cycles on x-axis and the engine numbers on the y-axis. So this particular engine here, engine number 1, has ran for a maximum time cycles of around 190 time cycles. And engine number 69 here, you can see 69 has ran for a maximum of 360 time cycles before, like 360 time cycles before it failed. And then this visualization here shows the distribution of the maximum time cycles of the engines. So we clearly see that there are some engines that are ran for 350, 360 time cycles, but majority of the engines have run for somewhere between 180 to 220 time cycles before they break down. And here, how do we get RUL? RUL is remaining useful life is first we get the maximum time cycles that an engine has run for. From that, when we subtract the current time cycles that the engine has ran for, it gives us the remaining useful life or the remaining time cycles that the engine will run for before it breaks down. So here we have that engine number 1, the remaining useful life is 190 in this particular run. And similarly for engine number 100, in this particular run, the remaining life is 0, which means that it is at its breakpoint. And here, and this is a visualization of correlation between the sensor data and the remaining useful life. And here is box plots of the sensor data. Clearly we see that the sensor data for each sensor is not very well distributed. It has many outliers, which means that we will have to scale the data later when we apply our algorithms, machine learning algorithms. And we don't have the real names of these sensors or the operational settings. So from the literature, I got these names, the real names, so that we have a clear indication of what these sensors mean. Like sensor 1, it means fan inlet temperature. So I just gave these names from the literature so that we have a clearer idea of what sensor 1 means and what the sensor 1 is describing or telling us. And these are some more visualizations of the sensor data as each engine is moving towards its breakpoint. So each color here represents a different engine, and as it is moving towards its breakpoint, what is the sensor data that it is showing? So right here it is fan speed, and as we see, as these engines are moving towards their breakpoint, the fan engine speed, the fan speed is increasing. And similarly, for various sensor data, I plotted these visualizations. And some of the sensors, they don't show any change in their readings. So these sensors, so some of the sensors which didn't show any change in readings are sensor 1, 5, 6, 10, 16, 18, and 19. So how is this useful for us right now? Because they are not showing any changes into their readings, it means that they are not useful for us when predicting our um, uh, remaining useful life. So that's where. And then, so here, as we have seen earlier, the sensor data is not very well distributed and also has many outliers. And so I did scaling, and then once we did the scaling, it has come, the sensor data is all come into bell-shaped curves, which means normal distribution. So now we can go ahead and apply our algorithms, linear regression, SVM regression, and also random forest regression. So here, first up is linear regression. So I fit my model and then I predicted. This function is here for evaluating my model here, and then train data set prediction, uh, test prediction, and validation prediction. So the R2 squared, which tells us the variability in data set that our model is able to explain. So R2 here for the training data set is 58%. For the testing data set is 56%. And for validation data set, it is a negative 11, negative 0.11, which means that it is not doing very well, which means that it is doing worse than a very basic average model. So this linear regression model is failing to predict uh, the remaining useful life. And next is support vector machine regressor. So this support vector machine regressor, for that the training set R squared is 60%, the test set R squared is 60%, the validation data set R squared is 56%, which means that on an average across train, test, and validation data sets, the SVM regressor model is able to predict 60% of the variability in the data, um, which is which is not very good. However, given that it is showing the same performance across train, test, and validation data set, um, it is okay. And next is random forest regressor. For random forest regressor, we observed that the train set has a good efficiency. It is it is 0.94 or 94, clearly 95%, which means that this model for training dataset is able to explain 95% of the variability in the data. However, when it comes to testing dataset and the validation dataset, the R2 squared is much less, which means that this model is overfitting and is not able to generalize. So, from the three algorithms that we use so far, the linear regression, uh, SVM regressor, and the random forest regressor, the SVM regressor is doing much better. However, it is only giving us an efficiency of 60%, but it is the same across the testing dataset, training dataset, and also the validation dataset. So, how we can improve the model is we have seen that these sensor data, the from these sensors, sensor 1, sensor 5, 6, 10, 16, 18, and 19, it is not changing. So it remains constant for all the runs, which means that they are not very useful for our prediction. So the next steps would be to remove these sensors from our data frame, uh, these sensor data from our data frame, and then try and applying the ML algorithms to see if the efficiency improves. Um, Thank you. That's my project, and thanks to Wasim Darbal from Kaggle, where I got most of the ideas from, and also Eric Lee from M2M Tech for very valuable inputs. Thank you.